is Trigonometry, section 3.2. So everything is starting to get really tricky now. Haha, just kidding. So, like I said, it's this big pile of information. So all this that we learned last time about the triangles, remember how I said it really applies to a circle, but you just imagine that this triangle connects the point on the circle to the center. And then the x value, how far to the left or right that dot is, would be the cosine, that adjacent, and the y value, how far up or down it is the sine. Now the reason I'm ignoring the hypotenuse in this case is because we learned in these problems with the letters right here that it didn't actually matter the variable how far out it was because that ended up canceling. So what we do is we usually look at things within the unit circle. So what that means is that it's a circle centered at the origin 0, 0 with a radius of exactly 1. So when the radius is exactly 1, the diagonal distance of the hypotenuse is 1. So then when you do the adjacent over hypotenuse, you just have the adjacent over 1. When you do the opposite over the hypotenuse, you just have the opposite over 1. So that's why the cosine is like the x value and the sine is like the y value. So if you just imagine trying to give the x, y coordinates of this point right here, you would go left and then up, just like a regular point, x, y. But all of these dots laid out would connect to make a perfect circle. Now there are a few dots in here, just like in our very first lesson, that are common. In our very first lesson, we learned about these special triangles for the 30, 60, 90 and the 45, 45, 90 because they tend to come up more often. So same idea within the unit circle, there are these angles that come up more often. So we learn the exact numbers for these guys right here, the exact coordinates. Now there's a pattern to it. I know these look like crazy looking numbers, but it's actually the same 5 numbers over and over. Now remember that the square root of 1 is 1, of course. So really, these right here are the square root of 3 over 2, the square root of 2 over 2, and the square root of 1 over 2, but we know that the square root of 1 is 1. And then this one right here, if you continue the pattern, the square root of 0 is of course 0. So this right here is the square root of 0 over 2. And then last, this one down here, it was 0, 1, 2, 3, so this one must be 4. And the square root of 4 is 2. And 2 over 2 is 1. So it's the same 5 numbers, 0, 1, 2, 3, and 4. But this one and this one clean up a little bit, they simplify. Same for this guy right here. Since the square root of 1 is just 1, we don't see the square root in this number. But it's really just 0, 1, 2, 3, 4, all connected right there. The same 5 numbers. Now notice that those same 5 numbers count down in the x value, 0, 1, 2, 3, 4, okay? And they count up in the y values, 0, 1, 2, 3, 4. And the reason I said down and up is because I'm looking at the angle that I used to reach that dot. So if this dot right here could be found by moving to the left this much, no, sorry, I'm backwards, the right this much, and up this much, let's go just find that as a decimal in our calculator. For some reason that really helped it make it click for me in the earlier days too. So if you punch in the square root of 3 divided by 2, it gives you as a decimal 0.866-ish. So let's just label that right here on this little chart, 0.8. Now I know that's very rounded, but just to give us an idea. Okay, 1/2 as a decimal is of course 0.5. Actually, let's do it on this row right here. And then the square root of 2 over 2, type that in to get it as a decimal. Square root of 2 over 2 is 0.707. So let's just name that 0.7-ish. Okay. So you can see that their literal decimal values, even though they look like weird, funny numbers, count up. 0, 0.5 is a little bigger, 0.7 is a little bigger, 0.8 is a little bigger, and then of course 1 whole is the biggest. So the x value of this blue dot would be the highest of these 3 dots because he is the farthest to the left. The x value of this red dot is a little bit lower, it's 0.7-ish. The x value of this blue dot is a little bit lower, it's 0.5. Now look at the y values, they increase. So as my angle goes from 0 up to 90, I reach first this blue dot, which is the lowest for the y value, 0.5. Then next I reach the 0.7-ish. This one is the highest of the three at 0.8-ish, till he got right up here at 90 degrees where he reached the radius of the circle of one whole. Okay, so the reason I'm trying so hard to make all these connections is because what seems like gibberish when you very first start it all has a bigger picture in mind. It's these same 5 numbers. And if you can memorize these 5 numbers, which are really, like I said, 0, 1, 2, 3, and 4, then you can do so much trig way faster than having to try to type stuff in your calculator. So this unit circle is something that you want to keep handy as you get started with these problems, because you won't have them memorized offhand. But the sooner that you can get these memorized, the better. That you can kind of visualize this as a point on the graph and the circle. It's going to really help make all those connections. So even though I'm going to show you kind of an easier way to get this answer, understanding why it's this answer was what's going to help. So like I said, it's this mountain of information, so come back to this video and kind of watch this again after you've tried some problems so you can see what I'm talking about with these 5 numbers right here. Okay, so bottom line, these points x, y represent the cosine and the sine. The cosine is the x, the sine is the y. C comes before s, just like x comes before y. So all of these labeled points, x, y, represent the cosine of that angle and then the sine of that angle. Okay, so let's fill in this chart here. What is the sine of the angle 0? So that would be the second value in the ordered pair, so it would be 0. What is the sine of the angle 30? It would be the second value for the angle 30, so it's 1/2 right here. The sine of 45 degrees, square root of 2 over 2. The sine of 60 degrees, square root of 3 over 2. And then last, the sine of 90 right here is 1/2. So that's how they got these numbers. Let's use this information to find the cosecant. Remember that the cosecant is 1 over the sine. It is the reciprocal. So if I flipped over 1 over 2, I would get 2 over 1, which of course is just 2. Okay, now if I flipped over 0, I would get 1 over 0, which would be undefined. Does not exist. That's why I didn't do him first. Okay, if I flip this over, 1 over square root of 2 is square root of 2 over 1. It's just the square root of 2. If I flip this one over, I would get 2 over square root of 3. And then last, if I flip over 1 whole, 1 over 1 is still 1 over 1. So it would stay 1. Now you may have noticed this one doesn't look like the chart, but it's really the same number. Remember that technically if you rationalize the denominator by multiplying the top and bottom by the square root of 2, then I would have ended up with 1 times the square root of 2, which is square root of 2, over square root of 2 times square root of 2 is 2. So 1 over the square root of 2 and the square root of 2 over 2 are exactly the same. So this right here is exactly equal to the square root of 2 over 2. This is the rationalized form, and this is the non-rationalized form, but they're the same number. So they pointed that out because that helps you see that when it's flipped over, in its more reduced form is the simplified square root of 2. Okay, so just kind of a heads up, they're the same number. All right, so here's a chart form of this same information right here. Notice that they just list it for these 5 angles in quadrant 1 with the 2 extremes of quadrant 1. Now if you expand into the rest of the circle, you get those same 5 numbers over again. The only thing that changes is their value, the sine value. Okay, and just like you would expect over here in quadrant 2, we have negative x's and we have negative cosines. In quadrant 2, I have positive y's, so I have positive sines. In quadrant 3, I have both negative x's and y's. In quadrant 4, I have positive x's but negative y's. So it all goes together. It all connects with what you know about graphing a point x, y. We're just connecting it to the angle from 0 that you would take to reach that point. It kind of connects into polar coordinates if you've ever dealt with those before. If you've had polar coordinates in a math class before, that is the same idea. Okay, so let's take it up a notch and see if we can use these values in our unit circle, the kind of established see-a-lot numbers, and clean up using order of operations something messy like this. So if I wanted 8 sine cubed of 30, well, remember that that's really 8, give me one sec, write it in the thinner pen, 8 times sine of 30 cubed. So this is another way of writing the same thing. So this is saying that the sine is cubed, not the angle 30. So not 30 cubed, the sine is cubed. So since the sine is cubed, I need to know what is the sine of 30. So here's 30 degrees. Sine is the second value, so it's right here, 1/2. We know from order of operations that I would need to do these exponents before the multiplication. 1/2 cubed is 1/8. 8 times 1/8 equals 1 whole. So the final answer of this simplified expression is 1. Okay, now this one, since they used the parentheses, they were trying to indicate that not just the cosine was squared, but also his coefficient, this number 4. So let's go ahead and use our order of operations. First, finding the cosine of 30. So here's 30 degrees again. Cosine is like x, so it's this first one, square root of 3 over 2. Now you may be thinking, I can punch cosine of 30 into my calculator. You can, but it's going to give you the decimal form, and you have to have this in exact form. You have to write it out with these square roots. Now I put parentheses around this cosine of 30 value right here, but just be careful because it's the whole thing squared, so I needed to close it twice. So first, inside of the parentheses, there is a multiplication. So this multiplication happens before the exponent because it's all together in a grouping. So the 4 and 2 would reduce. So this would be 2 square root of 3. And if I'm squaring that whole thing, I square both the outside number, 2 squared is 4, and the inside, square root of 3 squared is just 3. Okay, and then the outside number 4 times the inside number 3 makes 12. Now this one's sneaky because it's again all together squared, so I need to first find the inside stuff and then square it. But you're going to find something sneaky happens. Tangent is cosine over sine, so tangent of 45 degrees right here, this is sneaky, because I have to do the sine of 45 degrees, square root of 2 over 2, divided by the cosine of 45 degrees. Well, that's actually the same thing, square root of 2 over 2. So that means anything divided by itself is going to be 1. So I know in my next step, this first number is really just a 1. Okay, but tangent of 60 degrees is going to be sine over cosine. So it's going to be the square root of 3 over 2. I can scoot this up a little more. Square root of 3 over 2. And then the cosine is 1/2. This whole thing squared. So like we talked about, this first number is just going to reduce down to a 1. The second number is not a 1, so let's look at it a little more closely by doing our copy dot flip. Remember that when you're dividing fractions, you multiply by the reciprocal. So these 2's end up canceling. So I have 1 plus the square root of 3 squared. Now what's a little bit weird is these cannot be combined since he's an outside of the square root number and he's an inside, and I'm trying to add these two different d square root numbers. They cannot be combined. So instead, I I know it seems weird, but I actually need to FOIL this. It means I would have 1 plus the square root of 3 2 times the whole thing. So when I FOIL that, I get 1 times the square root of 3 is square root of 3, square root of 3 times 1 is square root of 3, and then last square root of 3 times square root of 3 is 3. 1 plus 3 is 4, and the square root of 3 plus another square root of 3 means there are 2 identical square root of 3's. So this is my final reduced answer. Okay, so since I had tangent, I had to do sine over cosine. Since it was all in parentheses squared, I needed to FOIL it out. Okay, when I am dividing fractions, I do that copy dot flip. I flipped the bottom one, the reciprocal right there. Now this one, notice it's the tangents being squared, not the whole quantity. So let's see how this one works. I've got the same tangent of 45 and the same tangent of 60, so I've actually already found those. So that would be 1 and square root of 3. Okay, so this time it's the tangent itself that's squared, so 1 is squared and the square root of 3 is squared. So this one would actually just be 4, much easier. Okay, so don't worry, it's really overwhelming at first, but like I said, it's really just plotting a point, x, y. So this one is the farthest right and the shortest. This one is the highest, but the farthest left. Well, the least far to the right. So use those decimal approximations. That really helped me out. Now last, there are the cofunction identities. So not only these right here have these kind of matching pairs, but all cosines and sines, since we have this circle, this relationship, where all of the points increase in their y values as they decrease in their x values, there's a pattern where you can find that same exact matching number by doing a 90 minus. So the corresponding sine to a cosine would be exactly 90 degrees higher, I think is how you say that. But basically, if you took 90 minus the theta, then you would get the exact same cosine value as the sine value of original theta. Okay, so we have this correspondence here. As the y's increase, as it goes up, the cosine x's decrease, and it goes in this big circle. All right, so knowing this, if I wanted to switch a sine of 84 into a cosine, my sine button's broken on my calculator, whatever the reason, then I can do that by saying that would be exactly the same as cosine of 90 minus 84. Make sure you get that 90 in the front. It's not 84 minus 90, so that means it would be the same as cosine of 6 degrees. And you can even test this in your calculator. So if I typed in sine of 84, make sure you're in degree mode, and then typed in cosine of 6, I should get that same exact decimal number both times. Okay, cotangent going to a tangent. Well, if you have the cotangent, let's just do this, of 90 minus the x value, okay, well, that one has it in the 90 minus already, so you can probably guess that it's just going to be tangent of x. That's true, but let's just double check using our function here. So I know that it would be tangent of 90 minus whatever angle this is. So just to double check, let's do 90 minus whatever that is. And then sure enough, if I distribute this negative, that would be tangent of 90 minus 90 plus x. So that confirms that it would be the same as just tangent of x. Okay. All right, and then just to double check, let's see what 90, let me change colors, minus 52 is. And you'll see that it is 38. Since 90 minus 52 is 38, 90 minus 38 is 52. Let's punch these into our calculators. Cosine of 52 and sine of 38. And we see again that they get the exact same value, this weird decimal of 0.61566. And we typically end it at 4 decimal places because back in the day before they had awesome calculators, they had big messy charts that always had 4 decimal places. But just for extra accuracy to make sure we're on the same page, this is the decimal I got from the calculator. Okay, so that is 3.2. Like I said, after you get deeper into text, you may want into trig, you may want to come back and rewatch this video and try to make that connection because it's all about this unit circle. It's a super big deal. But it'll take some time, so soak it in, get the answers kind of just cause I said so at first, and then the farther you get, the more it's going to make sense.